Hey kiddies, today we're going to be talking about molecular geometry. And what I mean by that is we've got to be able to take our two-dimensional drawings, our Lewis structures, and use that to perceive what the three-dimensional shape of the molecule actually is. So let's get started on that. We're going to be using something called the Vesper Model to take our Lewis structures and create these shapes. This Vesper stands for the valence shell electron pair repulsion model, which simply states that when we have these pairs of electrons, whether it's a bonding pair or a non-bonding pair, they're going to repel one another because they have like charges to be as far away from each other as possible around that molecule. That repulsion is what's going to dictate the shape of the molecule. We'll have our molecular geometry. So let's start with the simple Sp hybridization. That would mean two regions of density around our X. So maybe a double bond here and a double bond here would represent our X geometry. What would this look like in 3 dimensions if those two bonding pairs are trying to repel one another? Well, we can use this PhET simulation to add 2 double bonds. Now, as you see, we end up with a linear molecule. 180-degree bond angle. And the shape is linear. Let's move to our Sp2 hybridization. 3 regions of density. So we really have 2 choices here. We have 2 bonds and a double bond, or 2 bonds and an unshared pair. Let's take a look at the geometry of those 2 possibilities. When I have a double bond and 2 single bonds, we end up with a 120-degree bond angle. You'll notice this thing is perfectly flat. We call that planar. It's a 3-sided planar object, thus we have the shape trigonal planar. Our other choice was when one of these bonding pairs is substituted by a lone pair. Now when we consider the geometry, we don't show that lone pair. We don't consider that in the geometry, though it's actually there hogging space. So it's important to understand that our geometry, while electron geometry remains in that trigonal planar shape, we end up here with a molecule we simply call bent. So we don't really consider, I kind of just pretend those aren't there, but they are there when I'm thinking of the shape. We end up with a bent molecule in Sp2 with an unshared pair. When we're dealing with our Sp3 hybrids, we actually can have 3 different shapes here. 4 bonding pairs, 3 bonding pairs and an unshared pair, and 2 bonding pairs and 2 unshared pairs. So those would be possibilities for having Sp3 hybridization in our central atom. And we would end up with this fun shape here. The shape of this is called a tetrahedral shape. So even though it's drawn to kind of look square, if you start rotating it around, you can see that it's actually a 3-dimensional tetrahedron. The bond angle here is actually 109.5. A very fun geometric proof to go through. I'll be glad to go over with you sometime if you'd like. But that's our tetrahedral shape. If one of those becomes an unshared pair, you'll notice that it's gone from trigonal planar to adding that pair pushes those bonds away, that valence shell electron pair repulsion. I'll show that again. That's a trigonal planar. When I add that unshared pair, it pushes them away. And again, we don't consider the geometry of that lone pair. What we have here is a trigonal pyramid, a 3-sided base that is pyramidal, trigonal pyramidal. Now, if I substitute one of those bonds for another unshared pair, like our 3rd Lewis structure, we're still at Sp3 hybrid, but we end up back to a bent shape. And again, our bond angle is 109.5. Probably a little bit less due to the fact that that unshared pair is hogging a little more space, but you get the idea. We have a bent molecule at Sp3 with 2 unshared pairs. When we have an Sp3D hybrid, that means 5 regions of density. So I've created 4 different Lewis structures. Here we have 5 bonds, 4 bonds and an unshared pair, 3 bonds, 2 unshared pairs, 2 bonds and 3 unshared pairs. So those are all possibilities for having a central hybridization of Sp3D. Let's take a look at those shapes. All right, so there we have what we call the Trigonal Bipyramidal shape. It's called Trigonal Pyramid. It's trigonal because if I look down this axis, it's a three-sided pyramid, kind of like the Mercedes-Benz side. But if I tilt that up, you'll notice that it's like a pyramid sitting on top of another pyramid, bottom to bottom. Each one is each one's a trigonal pyramid, so we call this Trigonal Bipyramidal. Our bond angles from one side to the other is 90, but obviously looking down at this angle, it becomes 120 degrees. Trigonal Bipyramidal, 5 bonding pairs. One of them is substituted in for a lone pair. What do we have? We have this happy little guy. Looks like he's going for a little run. This has the technical name of seesaw. So I guess you can imagine that it's a little kid running to his mommy shape. We call it seesaw, I think, little kid running to mommy. If I substitute a unshared pair in, again, I pity the fool that doesn't know this shape. That's a Mr. T reference. Hey, it's T-shaped, letter T. Substitute a bond for an unshared pair to get our last. Hey, we're back to a linear shape. So the Sp3 hybrid is going to give us the choice of 6 bonds, 5 bonds in an unshared pair, 4 bonds, 2 unshared pair, 3 bonds, 3 unshared pairs, or 2 bonds and 4 unshared pairs. The geometry would look like this. 6 bonds. We call this shape octahedral because if you looked at each of these as a face, you'd end up with 8 faces. All the bond angles are 90 degrees throughout this whole shape. Now, it looks like jacks. I don't know if you guys ever played jacks as little kids, but that's kind of their shape. Now, our octahedral shape, when we add an unshared pair, now we end up with a pyramid. I'll take that lone pair away so you can kind of see it. It's a pyramid, but it has a square base. So we call this square pyramidal. If we substitute a bond for an unshared pair, it will go on the opposite side of the other unshared pair, creating a square planar molecule. Again, it's perfectly flat, but those electron pairs are on opposite sides, canceling each other out. We end up with a square planar geometry. Substitute another pair in, and we're back to our T-shape. I pity the fool. T-shape. 3 unshared pairs, 3 bonding pairs. And our last shape, with 4 unshared pairs and 2 bonding pairs, is back to linear. Of course, we're at 180 degrees there. And that concludes all the possible shapes we can have. So I'm going to include a link to this PhET simulation for you to practice, but it's important to be able to take that Lewis structure that we have, see where those bonds and where the unshared pairs are, and visualize these shapes. A 2-dimensional drawing into a 3-dimensional object. Thank you very much and have a great day.